All right, let's go ahead and talk about intermolecular forces. So far what we have been covering is how to draw Lewis structures for covalent compounds. And then we also looked at how to determine the shape of it due to valence shell electron pair repulsion theory. We've also looked at polarity and how to determine if a molecule is polar or nonpolar. Now let's keep building on all of that by talking about intermolecular forces. So intermolecular forces, also from here on out, I'm just going to call that IMF, is the force of attraction between molecules. So this is different than intramolecular force, which is the attraction of atoms or ions to each other. Now, intramolecular forces are much stronger than intermolecular forces, and intramolecular forces do help to define the properties of a substance. And what we're going to see is that intermolecular forces also help to define properties of substances, especially things like boiling points and melting points. IMFs are found oftentimes in solids and liquid phases of molecules. So here is a chart that kind of shows you this scale, this range from intermolecular forces to intramolecular, going from very weak forces to very strong forces. So we see that the only time that you're going to have zero attraction is in ideal gases. Otherwise, we see some of our intermolecular forces here, and we're going to talk about all of these in detail in just a moment. So our weakest is what is often called London dispersion. And then we see that we have dipole-dipole, and then that is followed by hydrogen bonding, which is very similar in strength to ion dipole. Now we see that our intramolecular forces are much stronger, and our strongest is going to be that ion. So any ionic bond is much stronger than a covalent bond. And our polar covalent is going to be stronger than our nonpolar covalent bonds. All right, so let's go through these IMFs. And there are four different types of IMFs. There's the dipole-dipole, hydrogen bonding, London dispersion, and also ion dipole. In order to determine which IMF is holding the molecules together, you need to know if the molecule is polar or nonpolar. And I've included a little chart here to give you some other ways, some other information about IMFs that we're going to go through in just a moment. Now, don't forget from the last video that I had made that this lowercase delta, that means partial negative. And then when we see the positive sign with the lowercase delta, that means partially positive. All right, so let's start off talking with the dipole-dipole. Now, dipole-dipole acts on polar molecules only, okay? Since there is a partial charge on each part of the polar molecule, which we see here in HCl, hydrochloric acid, we see what ends up happening is that the molecules orient themselves so that the negative end of one side is oriented and attracted to the positive end of another. So what we have here in this dashed line, that is our IMF. And in particular, this IMF would be dipole-dipole. Now, the dipole-dipole can vary in strength. And the greater the difference in electronegativity between the two substances, the stronger the dipole-dipole IMF. And some of the properties that you get from these dipole-dipole intermolecular forces is higher boiling and melting points, because it's going to take more energy to break a strong IMF. All right, the next one we're going to talk about is hydrogen bonding. Now, hydrogen bonding is this subset of dipole-dipole. It's a special kind of dipole-dipole. Now, I know the word bonding is used here, and unfortunately, I wish that that wasn't its name, because it's not a type of bonding. It is a type of IMF. This is a type of dipole-dipole that is very strong, and it is very specific to, let's see if I can get the pen to work here. This is very specific to hydrogen. Nope, it's not going to work. Okay, so this is very specific to bonds between hydrogen and fluorine, or hydrogen and oxygen, or hydrogen and nitrogen. And the way that I've told my students in the past to remember this is that hydrogen just wants to have fun. F-O-N. Okay, so you need to just memorize that if you see hydrogen bonded with one of those three elements, then it's going to be specifically hydrogen bonding intermolecular force that is between those. And the reason why it's only these three particular elements is that there's a very large electronegativity difference between these elements and hydrogen. And besides that, they're also very small atoms. So therefore, the hydrogen and the fluorine, or the hydrogen and oxygen, or the hydrogen and nitrogen can be very close together. And this is a very important bond to life. Hydrogen bonding is what holds water molecules together. It's what gives water all of its really amazing and unique properties, such as surface tension, the fact that it can take a long time to evaporate, the fact that water in its solid form is less dense than it is in its liquid form, and so ice floats. So this is a really, really important quality for life. We all need hydrogen bonding in order to have life on planet Earth. Besides water, hydrogen bonding is also the intermolecular force that holds the base pairs in DNA together. All right, so our third type that we're going to go through is London dispersion. And London dispersion is the only IMF holding nonpolar molecules together. So if you have drawn your Lewis structure and you have determined that a molecule is nonpolar, the only IMF acting to hold those molecules together is London dispersion. Now, London dispersion is also felt by polar molecules as well, but it's outweighed, like the strength of your dipole-dipole, or the strength of your hydrogen bonding is much stronger, and so that is going to be what gives those molecules more of its properties than the London dispersion force acting on it. But for your nonpolar molecules, the only IMF they feel is London dispersion. So London dispersion is very interesting because this all happens a whole lot faster than I can explain it, but it's an instantaneous momentary dipole. So, we have these electrons and they're swarming around the nucleus in this electron cloud. And sometimes these electrons will all tend to kind of bunch together, to clump together, and in one part of the atom. And when they do that, they cause this temporary dipole to form. And so when you have them all clumped in one area, you're going to have this temporary, momentary, partial negative area, which is then kind of almost like in this chain reaction, almost like this domino effect. Then a molecule that's close by will then, the electrons in it will be repelled, and so it becomes partially positive on that end, being attracted to where there is this clump of electrons that have caused this partial negative. I have a video at the end of this presentation, and I highly recommend that you watch it so that you can see Professor Dave's animation of it, because I think this would make more sense if you see an animation, a computer-generated animation of London dispersion. Okay, so your nonpolar molecules that only have this London dispersion for its IMF, they often have very low melting and boiling points. Now, just like dipole-dipole can vary in strength, London dispersion can also vary in strength. And the ways that you can vary that strength is in two different ways. You can increase the strength of the London dispersion as the molecules, excuse me, not the molecules, but the atoms that make up the molecule get bigger. And also by the shape of the molecule. So we see in the picture I have here that when you have a long straight chain, you have more surface area. So there's more contact that can happen between molecules, and therefore you can increase the London dispersion. As compared to the molecule over here, in which we see it's all balled up, there's not as much surface area, so we're going to have a much weaker London dispersion force that holds together all the different neoentane as compared to the neopentane. All right, and last but not least is our ion dipole. And so this isn't really between molecules, but this is actually between a molecule and an ion. And lots of times when we talk about this ion dipole, this is used to describe how ionic compounds dissolve in water. Okay, so we have kind of a classic example here. We have a salt crystal, so this is just table salt, sodium chloride, NaCl, and then we have water. And so if we say that we take this little salt crystal and we drop it into a cup of water, what happens is that the water will just come and start surrounding and breaking off all the different ions that make up our salt crystal. And what we see is that all of the partial negatives, so all of the oxygen ends of the water molecule, will surround the positive ion, the sodium ion, also known as the cation ion, okay? And then vice versa. All of the partially positive hydrogen ends of the water molecule will surround the negative ion, the anion, and in this case that is a chloride ion. And when we have the water molecules surrounding each one of the different types of ions, we call that a hydration shell. All right, so this is the video of Professor Dave Explains Intermolecular Forces and Boiling Points. It's a great video. He has one little error in it in which he says that London dispersion intermolecular forces are also called van der Waals forces. That is not true. Van der Waals forces is a general umbrella term that describes all three of the dipole-dipole, hydrogen bonding, and London dispersion. So every time he says van der Waals, I want you to just instead think London dispersion. But he makes so many other good points, and he does such a fabulous job of showing how these intermolecular forces affect the melting and boiling points of substances that I really wanted to include this video into the presentation. So I'm going to take this presentation, I'm going to put it into y'all's OneNote so that you can click and watch Professor Dave talk about these different types of IMFs. And then please do yourself a favor, look at those problems he has at the end, press pause on his video, work them out yourself, and see how you did. And as always, if you have any questions, please feel free to email me or talk to me at class. Bye.